Hello and welcome back to PC Retro Programmer. Today's video is another advanced video in our CGA graphics programming series, and as such it depends on information in the previous video on linear addressing. As I've already given the standard disclaimer for an advanced video at the beginning of that one, I won't repeat it here, but needless to say there is some background knowledge required for these. So the previous video was about linear addressing in the CGA mode 4, 320 by 200 4-color graphics mode. And by linear addressing we mean that all of the scan lines would be consecutive in video RAM instead of having the normal situation where all of the even scan lines are in the first half and all of the odd scan lines are in the second half of video RAM. It's my hope that by developing a linearly addressed graphics mode we can actually speed up a whole load of graphics primitives which are currently slowed down by having to switch banks back and forth on a regular basis. So at the end of the previous video we showed that linear addressing is certainly possible, but we ended up with the same frame repeated twice on the screen. And the reason for that is because we're now using one scan line per character instead of two in the CRTC settings. And this means that in order to fill an entire screen, we need to count 200 characters in the vertical direction that are going to be displayed and 262 characters in the vertical direction for an entire CRT frame. The problem is the CRTC only has a 7-bit register and so maxes out at 127 for counting characters in the vertical direction. So I've developed a technique for tricking the CRTC into wrapping around and resuming the count from 0 before it reaches the total that we're interested in. Now, the problem with this method is that although I've demonstrated it on an improper mode, and it does work there, when I asked some CGA experts about this, well, one of them said that they didn't think they knew this trick, and that could just be my poor explanation of it, or perhaps the trick just doesn't work. The other expert said that although he believes the trick should work on any genuine CRTC hardware, he doesn't understand how it will help linear addressing. So his comment was that if you want to set up a 320 by 200 4-color graphics mode with linear addressing, you need to output row address 0 in the top half of the screen and row address 1 in the bottom half of the screen. Now I don't currently understand exactly what he means by this, and I guess that's what we're trying to research in today's video. I've deliberately recorded the introduction before I've tried it myself in a graphics mode, and so we're either going to find out what he meant by this and learn something new, or we're going to demonstrate that the technique actually works, in which case, yippee, we'll have a linearly addressed graphics mode. So I think the outcome will be interesting either way, so let's get stuck in. Well, I decided to draw this diagram representing a CRT frame, and roughly speaking this is what you see when you look at a monitor. There's a central region here which has all of the pixels that are displayed. There'll be 320 by 200 of these in CGA mode 4. And of course around that you have the border region. And actually this particular diagram also includes some extra space, drawn entirely perfectly to scale of course, for the time that it takes for the horizontal retrace to occur, where the electron beam quickly whips back to the left-hand side of the screen for the start of the next scan line, and also the vertical retrace where it whips back to the top left corner. So think of this more as a timing diagram rather than a layout, but it is designed to look like a monitor. Now from the CRTC's perspective, everything actually begins here at the beginning of the active region, which is what we call this middle portion where all the pixels will be displayed. And in fact sometimes this entire diagram is drawn with this point at the upper left corner and everything else permuted about it, so that everything appears from the point of view of the CRTC. But I wanted things to look like a monitor here, so this is the diagram we have today. And what this means though is that a scan line begins on the left-hand side of the active region, runs across the diagram here and finishes at the start of the next scan line. So that's the CRTC's view of the world. Now what we want is for there to be 200 scan lines in our active region and 262 is the number of scan lines that we need in total because that's the standard for CGA. Now the way this normally works is that you have 2 scan lines per character and you just put the number of characters in the vertical displayed register. So in our case that would only be 100 characters, and so we put the value 100 in the register. And there's no problem fitting that, it's a 7-bit register. But in the case of linear addressing, we want 1 scan line per character, and so now we need 200 characters for the displayed portion, and we need a value of 200 in the vertical displayed register, and that won't fit in a 7-bit register. So that's our first problem. And the same happens with the vertical total. Normally you put a value of 127 in, and it starts counting characters from 0, so 0 through 127 is 128 characters, and if they're 2 scan lines high, that's a total of 256 scan lines. That's not quite up to 262, and so there's this additional register called the vertical adjust, which only counts scan lines, not characters, and you can put a very small value in it, so an extra 6 in this case would take us up to the 262. So that's how it normally works, but again, with 1 scan line per character, we actually would need a value of 256 minus 1, which would be 255 in the vertical total register, and that's not going to fit. So what we really need the CRTC to do is to count all the way through its range from 0 to 127 once without doing anything, and then basically wrap around and then count out to the full values that we want. So in our case, we would need it to count up to 127 in the second time around for the total, and we need it to count 72 scan lines for the displayed the second time around. So this is not that difficult to achieve, and the reason is the CRTC is an incredibly simple device. You should think of it as internally just consisting of a bunch of counters. So these are just automatically being incremented, and it certainly has counters for vertical character counts. And so basically it also has some registers which you set values in, and the only thing the CRTC can do is compare equality between the counter values and the values you set in the registers. Now, the equality will trigger actions. So for example, if it reaches the total number of characters for the displayed region, then that will trigger an action which is to turn off the pixel information. So it no longer reads pixels from video RAM and just outputs the background color. And similarly, when it gets to the value for the sync pulse, then when equality is reached, it outputs a sync pulse. And similarly for the vertical total, it will go into the vertical adjust period, and once the vertical adjust period is finished, then it finishes the frame and starts the next one. So this is the way that the CRTC works. So in order to get it to ignore everything on the first trip around as it counts from 0 to 127, we just need to make sure that equality never happens. Now you might wonder, how are we going to do that, since we have to set the registers to some value between 0 and 127. Well, it turns out what we can do is initially set the value to 127, and it will just merrily start counting towards 127, but before it gets there, we'll change the value from 127 back to some earlier value that it's already passed. So it can't hit equality with that value. So once it gets to 127, absolutely nothing happens. And what happens when you increment a 7-bit register that's at 127? Well, it just goes on to 0. So it just keeps counting. And once it's down here, this value that we set it to is actually corresponding to something down here. So it'll keep counting towards that, but before it reaches that, we'll set it to 127 again, which will be up here, and it will just keep counting until it finally reaches that. Then, for the first time, equality occurs, and it triggers the adjust period, and finally the end of the frame. So that's basically what we're going to do to deal with the vertical total. The vertical displayed is exactly the same. We set it to 127, it counts towards it, we move it probably to the value 72. Once it gets to 0 again, that actually corresponds to here, and it will just count down to 72 and stop displaying pixels. The sync pulse might be a little bit more complicated. My experience so far is that there are some inequalities between these values that may need to be respected. And we'll see if we run into that today. We may not. It depends on what you're actually trying to achieve. But assuming we can set the sync pulse to 127 initially, we will. It'll count towards it. We'll move it to a value which, when it gets to 0 here, actually corresponds to where we really want the sync pulse. And so that's all there is to it, basically. Now, of course, this means that we need to set values of registers at specific times when the actual monitor is displaying things on the screen. So fortunately, there's actually a way to deal with this, and that is because the CGA card offers support at 03D AH, which we can monitor, and it tells us in one of the bits, it will get set to 1, we're in the vertical retrace period. And so that means we can detect the vertical retrace. One of the other bits will get set to a 0 when we're in the active region. So what we do is we first wait for vertical retrace, then we wait for that other bit to go to 0, which means we must be in the active region again, and so we must be in here, and then we can actually change some values. But in order to not have to count scan lines every time, what we're going to do is we're going to set up some programmable interval timer interrupts. So it can be set up to count pulses, and it actually uses the same clock, although it's adjusted with a slightly different multiplier. It uses the same clock as the CRTC, so it can be made to line up precisely with the CRTC. So what we'll do is once we first reach this point here, we'll set a programmable interval timer interrupt to fire off, and we'll set a value of 19,912 in the programmable interval timer, and that is the exact number of pit cycles that a CRT frame takes. Now actually we really have to have some other interrupts fire at other times as well, and so really it's the total of the 3 or 2 or however many regions we need that have to add up to 19,912. But basically we'll fire off interrupts at the right moments when we want to change the register values every single frame, and the PIT will just keep doing this for as long as we let it. And this is going to fire interrupts, which we can then intercept with an interrupt handler, and those interrupt handlers are what's going to change the register values. And all of that's just going to be happening in the background without our intervention once we set it going. And so then we're free to use the CPU to do whatever we want. Now you do have to be a little bit careful. The interrupts can occur at any time. For example, DOS likes to fire off interrupts for the real-time clock. That probably won't be a problem for us because we've taken over the programmable interval timer. But again, if someone presses a key on the keyboard, an interrupt occurs, for example. So this is something we need to look out for. You can actually end up in unstable states and lose sync on the screen just because there was an interrupt fired at exactly the wrong moment and you ended up with the register values being set incorrectly at the wrong time. It's not going to be much of an issue for us today. The only thing that we do have to get right is that we need to change to 1 scan line per character in this first scan line. If we do it any later, we will have been using the wrong value up to that point. If we do it any earlier, then it'll mess up the end of the last frame. So we really need to get that right in here. But then after that, I think everything's a little bit flexible. We just put things roughly in the right place and everything should be good. So I don't see any problems with this approach, but the only way to find out is to try it and see. So let's write some code and see what happens. Well, before we jump into our main project here, what I want to do is set things up so that we can actually see what's going on. So Linear4 is basically our original linear addressing code, but I've made a few changes to it. So the first thing is, instead of drawing the diagonal pattern on the screen that we had previously, I'm going to draw a line on the left-hand side of the active region and also one on the right-hand side. So for each of the 100 scan lines in the active region, I'm going to put a pixel on the left-hand side and then skip over all the other bytes and put a pixel on the right-hand side of that active region. So that'll allow us to see exactly where the active region is. Then what I'm going to do is just iterate through 10,000 frames just so I've got long enough to actually look at the picture. And the first thing it's going to do is wait for the vertical retrace. Now this is done by looking at bit 3 of port 3DAH, and basically we need to wait until that's a 1, and then that'll be the vertical retrace region. And when that happens, I'm then going to set the background color to green. So we just decrement DX, so we go down to port 3D9H, and that's where we set the background color, and we'll set that to 10, which is green. So then we're going to check for the end of the vertical retrace period, and when that comes, we set the background color to red. So that means that we're actually going to be able to see where the vertical retrace period starts and ends. So then we've got 100 scan lines to go through, and basically what I'm going to do is wait for the beginning of the first scan line. And so this is just bit 1 of 3DAH, and we want that to become a 0 because that indicates that we're in the active region. So the first time that happens, that'll be the first scan line, and then I'm going to set the background color to blue at that point. And at the end of the scan line, when the bit 1 becomes a 1 again, it's going to set the color to magenta. So we'll be able to see the extents of the scan lines. Basically we'll be able to see when we've detected that we're in the active region and when we've detected that we're no longer in the active region. And so it's just going to loop through 100 of those scan lines, and then the whole thing will repeat again for the next frame and so on for 10,000 frames. So once all that's done, of course, it just does the usual thing of waiting for a key press, restores the text mode and exits to DOS. So let's run this and see what we actually have on the screen at this point. Now, when I run this code, you'll see that it's really quite busy. So first of all, we have vertical lines at the beginning and end of the active region, as we expect, and of course there are 2 frames on the screen at the same time, as we had previously. But what you'll also notice is that we're not detecting the beginning and ending of the active region on each scan line exactly when we expect to. You can see that we're actually detecting both of these a little late, and so the palette is not going from magenta to blue until well after the beginning of the active region. Now this is because of the code that we're using to detect that. Each iteration of the loop takes some time to run, so if the first time the loop runs it doesn't detect that we're in the active region, then it needs to do another iteration of the loop, which takes really some cycles. And so at some random time it finally gets a yes, we're in the active region, and the palette changes. The same thing is happening for the vertical retrace. You can see a little bit of green seeping at the bottom of a black region there, and this is because we're not actually detecting the end of the vertical retrace period immediately, and so there's still a little bit of green there. Now we might expect the whole vertical retrace period to be green, but actually the CGA card blanks this region. The vertical sync pulse is actually 16 scan lines in width, and that is actually where the vertical retrace period is, and this is hardwired in to black out the screen for those 16 scan lines. on the CGA card. So you will see that there's a red portion after the vertical retrace period, and this is the time between the end of vertical retrace and the start of the first active scan line in the next frame. So all the regions that we expect to be there are there, they're just not appearing the way that we might have initially thought. But what about all this flicker? Well, this took me a day to debug the first time I saw it and had me really puzzled, but it turns out to be a DOS interrupt that's firing. It uses the programmable interval timer to run the clock for the date and time, and this fires 18.206 times per second. And it really takes some time to handle, so every now and again you see two scan lines that are messed up, and this actually messes up our counting. And so this is why we end up with flickering, because it's waiting for scan lines that aren't going to come because we've lost count. So this is something we're going to try and fix in the next version of the program. We're going to try and intercept that interrupt handler ourselves and just do nothing so that it runs much faster, and see how that improves the program. So Linear4 is our attempt to try and intercept the DOS timer interrupt. Now normally you're supposed to do that at interrupt 1CH, but this actually won't stop DOS intercepting the programmable interval timer pulses, which is what it's using for its clock. In order to do that, we actually need to intercept the programmable interval timer interrupts themselves, and this is actually on interrupt 8. So basically we're going to substitute our own handler for this. So let me show you the handler first, which is at the end of the file here. And it really doesn't have to do very much. It just has to acknowledge the interrupt, which we do by sending 20 hexadecimal to port 20, and then it will just return using an interrupt return, the IRET instruction. And of course we're using the AX register, so we also need to save that. Every register that you use in an interrupt handler needs to be saved, because after all we're interrupting some other code, and we don't want to mess up the register values. So that's our handler. It's about as short as it can be. And then at the beginning of the file, all I've done is add code to replace the DOS handler of interrupt 8 with our handler. So we do this in the vector table at the very beginning of memory, and that has segment address 0, of course. So we move 0 into the DS register for this. And so interrupt 8 will be at offset 4 times 8. Each interrupt vector takes 4 bytes. There's a segment address and an offset address that's loaded into the vector table. And so the vector that we need to intercept is stored at address 4 times 8, or 32, in that first segment of memory. So we're going to replace the offset with the offset of our own handler, and of course we can just use the current code segment for the segment address for our handler, since our handler is actually in our code segment. And so that takes care of replacing the handler with our simplified one, which does nothing. Of course, we turn the interrupts off while we're doing all of this, just so that nothing weird happens while we're modifying the interrupt table. But that's all there is to it. Let's run this and see what difference it makes. So what we're looking for this time around is an improvement in the way that interrupt is being handled. And if you look very closely, it's now only one scan line that's being messed up every now and again. But we're still getting the flashing, and this underscores that when you're counting scan lines in this way, you either need to turn interrupts off entirely, or you need to have the interrupts firing at a time that doesn't interfere with that counting. Otherwise things are going to get messed up. The other minor change that I made here was to change when the sync pulse is firing. So it's now happening 9 scan lines after the end of the active region instead of the 12, and this just moves things about on the screen a little bit. So you can actually see that that vertical retrace period is really coincident with the sync pulse. And this is 16 scan lines, as I mentioned. Now, one other weird thing is happening now. The floppy drive light is now on permanently while this is running, and this is because DOS actually needs its timer interrupt to handle the acknowledgement for the floppy drive. And in fact, DOS really doesn't like its interrupt handler being taken over. So if you don't restore that to the original before the program exits, DOS will actually hang. So I'm going to make another few changes to the program. First of all, I'm going to require a key press to start it, and I'll wait for that floppy light to go off before I start the program running. And then I'm going to turn interrupts off entirely for the duration of the program so that we don't have any timer interrupts firing, and see how that improves things. And I'm also going to save the original DOS interrupt vector and restore it before I exit to DOS. So Linear4 is our attempt to fix the problems that we observed in Linear 3 that we wrote previously. So the first thing I'm going to do is wait for a key press at the beginning of the program rather than the end. We don't really need one at the end, it'll just exit to DOS immediately. And so this will allow me to wait some time until the floppy drive settles down before the program actually runs. The second thing I'm going to do is to actually save the existing interrupt vector from the vector table into a location in memory so that I can restore it at the end of the program. So then DOS won't get upset that its interrupt vector has been taken over. So because we're messing up the DS register here, I won't store this vector in the data segment. I'll store it in the code segment instead. And so I'm going to store the offset in a location that I've called IRQ off save, and the segment in IRQ seg save. So let's see where those are down the bottom of our program. That's where they are here. You can see there's a word for the offset and a word for the segment, and I've just put those immediately after the end of our program so they don't interfere with our code at all. So that will save the interrupt vector that's currently there before we put our interrupt vector in, and then at the end of our program we need to restore that again. So you can see that here we read it back out of the location where we saved it and put it back into the interrupt vector table, and that restores the original DOS interrupt handler that was there before we replaced it. So those things should take care of some of the issues that we're facing, but in order to clean up the image a little, we're going to turn off interrupts as well at the beginning of the main loop here, and we'll turn them back on again at the end of the main loop. So this means that there will be no interrupts running, not even our own interrupt handler for that DOS timer interrupt during the main loop. And so that should mean that we get a nice clean image without any flashing. So let's run this code and see how that looks. Well, let's try this out, Linear4, and now it waits for a key to be pressed, and the floppy light has gone out, so I'll press a key, and yeah, that looks really smooth. So now there's no flickering and there's no scan lines being missed, so everything's working the way that it should, and I've actually already run this code through, and it does indeed exit smoothly to DOS without hanging. So I think we've fixed all of the problems that we can fix for this version. So now it's time to move on to the main trick that we want to implement, which is the linear addressing with 200 scan lines. Of course, we're going to do that slightly differently using timer interrupts, which we'll set up at various points in the frame in order to change the CRTC registers at the appropriate times. So let's take a look at the code for doing that. So the code for our main trick is in Linear4 Asm, and it's basically going to start off the same way as our earlier code did. It sets up the CGA segment, waits for a key press, saves the old interrupt handler vector, the one from DOS, and puts our interrupt handler vector in the table. And this is where things start to be a little bit different. So first of all, we change into CGA mode 4, and then we wait for vertical retrace. Now the interrupts are still off here, so we're not going to get any nasty surprises. And then we wait for the first scan line of the active region, and we just do that by looking at bit 1 of port 3D and once that goes 0, we must be in that first active scan line right at the beginning of that scan line, hopefully. And so this is the point we want to set up our timer. So this is done as follows. First of all, you have to send a byte out to port 43 hexadecimal. This is the control byte for the timer. And this does a number of things. First of all, it tells it that we're counting in binary. It tells it that we are using timer 0. It tells it that we're going to be setting the value in the timer, the count, in 2 bytes, a low byte then a high byte. And it also tells it that we're going to set up a repeating timer. So basically, unless we change the value that's in the counter, it will just keep using the same value. And so this sets up a repeating interrupt that will occur regularly depending on what value you put in the counter. So here is where we're going to set up our initial value for our counter. And I've determined that I want the first interrupt that fires every frame to happen on the scan line 120. So I need to wait for 120 scan lines. So that's what I tell the timer to do. So it won't fire an interrupt until we reach that scan line. Now each scan line takes 76 timer pulses, and so if you work that out, that is a 16-bit value with low byte 160 and high byte 35. So we just send these consecutively out to port 40 in hexadecimal. We set the timer up to expect the 2 bytes one after the other. So basically what's going to happen now is our first interrupt is going to fire on scan line 120, and unless we make a change to that timer value, it's going to keep firing interrupts every 120 scan lines. Now that's not exactly what we want to do. There isn't actually an equal amount of time between the 2 interrupts that we want to fire every frame, and so we're actually going to need to do some additional work to change this timing value every time an interrupt fires. But we'll get to that in a moment. In the meantime, we need to get to work quite quickly while we're still on the first active scan line because we need to set 1 scan line per character. And this is done by setting max character scan line to 0 in register 9. So now we can relax a little bit because we actually have plenty of time to set the next lot of values. If we didn't get this one on that first scan line, then our count of scan lines would get messed up. But the other values aren't as critical. They just need to be done relatively soon rather than immediately. And so we can set the vertical adjust to 6 and the vertical total to 127, the displayed, and the sync position all to 127. So vertical adjust is in register 5, and then the other ones are in registers 4, 6, and 7. So this sets up the values that are going to be in force for that first portion between the first scan line and the first interrupt firing. Now the next thing we need to do is to put another value in the timer counter. Now this might seem a little bit odd since we just already set a value in the timer counter, but this time we don't set it with a control byte. And if you don't use a control byte, instead of immediately resetting the counter, what it does is it waits until that first interrupt is fired and then it uses this value. So this is basically the next value that's going to be used in the timer. And I've determined that I want 113 scan lines between that first interrupt that happens on scan line 120 and the next interrupt that I want to fire. So we're actually going to require 2 interrupts per frame, and each of those interrupts is going to have to set different values in the registers, in the CRTC registers. And so we're actually going to need 2 different interrupt handlers to deal with this. So more about that in a moment. But now that we've actually set everything up for that first interrupt to fire, and we've also set up the timer value that it's going to use after that first interrupt fires, we can turn the interrupts back on again, and we're now free to go about our business and let the interrupts fire at the appropriate time in the future. So let's scroll down now to where the actual interrupts are in the code. So here is interrupt handler 1, and this is the one that will fire on scan line 120. We save some registers, and then the first thing we're going to do is set the vertical total to 110, displayed to 72, and the sync to 95. So I've computed all of these values to be the right ones. And so these are the values that are going to be in force after the first interrupt is fired. So this is actually where I'm moving the values to a value prior to the scan line that we're currently on. So we're currently on scan line 120, and I'm setting all these to values that are lower than that so they don't get triggered the first time through the counter loop. So once that's set, then I need to set up the timer value for the next run through the timer. So this will be 149 scan lines, but the thing to bear in mind here is this is not the amount of time that these values will be in force. Those are in force from scan line 120 for 113 scan lines, and that's the value that we already set up. What we're setting up here is the amount of time that the next timer interrupt will fire after. And so this is the amount of time that the next lot of values will be in force. So then finally we need to switch over to a second interrupt handler. We're going to need to set different values on the other interrupt that needs to fire every frame, and so we need a different handler for that. And so this is called IRQ0 handler 2, and we set that in the interrupt vector table. We don't need to put the segment address in because that'll be the same. We just need to put the offset of that second handler in. And once we've done that, then this first handler can finish and do its interrupt return. So here is the second handler where the second lot of values get set, and this is the one that sets the values back to a vertical total displayed and sync position of 127. And this then has to set up the timer for the next interrupt that's got to fire. So again, this is not 113 scan lines that this slot runs for. This is the 113 scan lines that the next lot of values will run for. So once we've set up the timer for that, then we need to switch back to handler 1. So the two handlers are just going to hand off to each other. Basically one will fire, then the other will fire, and it'll just switch between the two. And one of them is going to take 149 scan lines, and the other one is going to take 113 scan lines. And if you add those two up, of course you get 262 scan lines, which is the total for a frame. So they're just going to alternate between the two handlers. So once this handler finishes, of course, it just returns just like the other one. So basically this is going to be going on in the background, and we don't need to do anything to keep this going now. This is sort of self-perpetuating. Each handler will set up the timer values and switch over to the other handler, and this will just go on in the background automatically. So now let's take a look at the main program itself. So let's scroll back up to where we left off previously, and you can see this is where the interrupts got switched back on after we did our initial setup. And now everything should be going on in the background without our intervention. So we're free to do whatever we want, and what I'm going to do is just put some values into video RAM so we've got something to look at. So I'll just use our standard trick of drawing some bars on the left and the right of the screen to show the beginning and end of each scan line. So we'll do 100 scan lines with white on the left and white on the right, and then we'll switch to another 100 scan lines that have different colors, so color 2 on the left and the right, which I think will be a magenta. So if everything is working, we should have lines running down the left and right of the screen, and the first 100 scan lines of which should be white, and the second 100 scan lines should be magenta. And so that should verify that we really do have a 320 by 200 linearly addressed mode actually working. After that point, I really don't care what happens. I'm really keen to see this work. And so I'm just going to hang. Basically, it's just going to be an infinite loop here. And if I didn't have this here, it would just immediately exit to DOS and we wouldn't see anything. So let's give this a try and see what it looks like. Well, here goes nothing. Linear4.exe, and it's going to wait for a key press. Floppy's finished, and away we go. And oh, look, so that's not what we want at all. Yeah, I see. So, well, we are in a mode, and it is stable, and there are certainly 200 scan lines on the screen here. But you can see that we have white lines that run down the left and right of the screen, just as we were expecting, and then we have a few pixels of magenta, which looks like the start of the second 100 scan lines. But at some point, it looks like 2 and a bit scan lines in, it suddenly changes back to white again, and it's in the middle of the screen instead of on the sides. So I think I see what's happening. So once it gets to the end of the first half of video RAM, that would be 8,192 bytes, which would be 100 scan lines plus an additional 2 scan lines plus an additional partial scan line. Then it suddenly switches back to using data from the first half of video RAM. Oh, that is annoying. So it looks like our expert was correct. Well, I may as well reveal who it is now, since he was 100% right. This is Reenigne. Yeah, I should also credit him. He sent some code to me a long while back now, and I've actually adapted portions of that in the code that I showed you today. He was helping me debug a problem that I had with my interrupt handlers, which I initially did in Turbo C. And it turns out that it doesn't really handle these quite correctly if you access data outside the interrupt handler function. So it's probably better to do those things in assembler anyway, and then you've got more of an idea of exactly what's going on. But at any rate, this is really a bit of a disappointment. So it means that we have linear addressing, we have a 320 by 200 4-color mode, but it screws up where it gets the data from once it reaches the end of the first half of video RAM. And I think I see why now. So of course, we're telling it to always use even lines because we're using the first scan line of characters only. And if we're only using even scan lines, it must be set up to only take data for such scan lines from the first half of video RAM. And that entirely explains what's going on here. So once it reaches the end of the first half of video RAM, it just wraps around. And that happens at exactly 8,192 bytes, which is exactly the position of the top of that bottom white line that goes down the middle of the screen. So this is really quite annoying. But not all is lost actually. So what it means is that we could do a smaller mode that only uses data from the first half of video RAM. So I think if I'm calculating this correctly, we could take a horizontal width of 256 pixels, which should be 64 bytes per scan line, which should actually be a very nice value to use as well. And then we could do, I think, 128 scan lines of that. So we'd end up with a mode that was 256 by 128 pixels, which might not look too bad. And that would only use data from the first half of video RAM, so we'd get around this problem. So we could use our trick, we'd have linear addressing, and we'd have a mode. It'd just be smaller than the full screen. So that is what I think I'm going to do next. Try that out. But yeah, this is a very interesting result and not at all what I was anticipating. So this particular trick that I've shown today definitely works in one of the improper modes. And so that was why I was expecting it to work here. In that case, the CRTC just keeps reading linearly from video RAM. It doesn't wrap around at the end of the first half of video RAM. And so the interesting question now is, does it work in all of the improper modes? I certainly expect that it works in all text modes because those are linearly addressed anyway, and so it wouldn't make any sense at all if it didn't work there. But that's not the interesting application for this. Although I suppose if you were using a character height of 1 there, then you might also want to count more than 128 scan lines there. So you could still use the trick in a text mode perhaps. But yeah, it looks like in a graphics mode at least, it's not going to work the way we expected. So very interesting results. So I managed to code up that linearly addressed 256 by 128 for color mode that I was talking about. And it was pretty easy actually. All I had to do was change the vertical displayed in the second lot of figures down to a 0 from 72. And then at the very beginning of the program just to add a horizontal displayed value of 32. It's normally at 40, and 32 characters is 64 bytes or 256 pixels. So once it was working, I was able to just clean it up a little bit. I changed the data that goes into video RAM so that it's spaced 64 bytes instead of 80. And of course, I cleaned up the horizontal and vertical sync values so that everything was centered in the screen, more or less. And so this seems to actually work. For some reason, I get some timing issue every now and again. So when I run it, I usually have to run some other program beforehand. But that's probably because either the key press is bouncing and this is causing extra interrupts, which is messing up the timing, or it could just be that I'm trying to do too much on that first scan line, and I probably need to reduce that first delay just a little bit so that things start earlier on that scan line so everything fits. But at any rate, this is now just down to fiddling about until everything works. As you can see, I've got 64 lines now with white on them and another 64 with magenta, and so this is definitely a linearly addressed mode. It's much smaller than the full screen, of course, but I still think you could use this for at least a demo effect. You could certainly still use the remaining part of the screen if you wanted to, and you can certainly still use the remaining part of video RAM, just not in this particular mode. So you'd have to change the mode on the screen, and that's certainly possible. You could use a text mode, for example, or an improper mode, and maybe have a scroller running across the screen, something like that. So there are all sorts of different possibilities that you could combine this with. But even just on its own, the ability to do everything with linearly addressed data is going to mean that we can do some really fast primitives, animation and so on. So That's probably going to be the topic of some of the later videos on the channel.